Okay, so this is a continuation of the lecture on standard deviation and uncertainty in position. Okay, so let me write the uncertainty. So what will be the standard deviation if there is an uncertainty in position? So what will be the mathematics? So let me write the mathematics part and then I will explain. So it will be 1 by n. So consider there are n detectors at n positions. So as I mentioned in the earlier lecture, so consider the diffraction experiment and consider there are detectors at discrete positions. See what I'm saying is I'm saying there are position detectors at discrete position and say there are total of n detectors. Agreed. So although diffraction on screen will have a continuous pattern, but just for a moment you assume that you have kept the detectors at discrete position. Agreed. Now, so what will be the uncertainty in the position? Okay, so that will be 1 by n summation I. Okay, now what will be this? This will be the value of position xi where the electrons are likely to be found. Agreed. And then, so what is xi? So xi are the places where the detectors are kept, or xi are the positions where we will find the electrons. Agreed. So xi minus, and then there will be an x bar. So what is x bar? X bar is the expected value of position where the electrons will be found in more quantity. Agreed. That is x bar. We have discussed the value of we have discussed the expectation value in more detail in our last lecture. Agreed. So you know what is x bar. So this is the standard deviation. But now you will say, how is the standard deviation related to d? After all, you said that the deviation, this standard deviation sigma, is the um, measurement of the uncertainty in position. So if you look at the diffraction experiment, I stated earlier that the uncertainty in position is d. Agreed. Now question is, how are these two related? Okay. Now let me give you a hint. So the hint is, you see, if you measure, okay, so if you measure the, so what is the most expected value? So most expected value position is at the center. You all know. In diffraction, you see that most of the electron end up at the center. So the most expected value is at the center. Now, how much the electron is spreading around the center depends on the width of the slit. That you agree? Okay. For example, if the width of the slit is small, then what will happen? So if the width of the slit is small, then the spread of electron along the y-axis will be large. Similarly, if width of the slit is large, then what will happen? Then the spread of electron along the y-axis will be less. Okay. So somehow what you can see is that what are you measuring? You are measuring the distance xi from x. Then you are measuring x2 from x. On the other side, you are measuring xn from x. Then there will be an xn minus 1 from x. Okay. So when you are measuring these numbers, indirectly you are actually measuring the spread. Agreed? So indirectly you are actually measuring the spread. So using this data alone, you can actually guess the value of d. This is all I'm saying. That's why this particular quantity has the power to give you the uncertainty in position. This is just a rough idea where I have related the data on the screen. Okay, the data on the screen that you see on the right with the uncertainty in position, which is d, on the left. Agreed? So I hope you got an idea that yes, we can use this mathematical quantity to find the uncertainty in position. So can we write this in a better way? Yes, there is a good way to write it. So they say that the uncertainty in position x is equal to root over of, okay, so you can write 1 by n. So say n is the number of detectors, summation I, agreed. Then we have x I minus x bar and the square of it, agreed. So this is the uncertainty in position. Now we can write this in more better way. Okay, there is a good way of writing this. So let me remind you, um, what will be, so in the next step, so let us do, so what is uncertainty in position square? So if you do the square, you see that this quantity inside the square root can be also written as summation I, okay, then you have a square of what, x I minus x bar whole square, and then I will write here the probability of finding at position x I, okay, the probability of finding at position x I. So now you would say that why have I written probability? Okay, what on earth gave me the permission to write the probability? So the answer is, we have already discussed this part in our lecture where we have discussed expectation value. So I'm not gonna say anything more. Okay. Now question is, there is a way where we can simplify this term to this following term. So where you have uncertainty in x square can be written as um, the expectation value of x square minus the square of expectation value of x. Okay, quite an interesting result. So now what we'll do is we'll derive how we got from here to here. Okay, but before deriving that, let me tell you something, what we did. So in conclusion, so point number one is, look at the left hand side diagram. Point number one is, we discussed what is standard deviation in statistics using this particular data of 4 students, and we calculated the standard deviation here. And what we stated? We stated that the standard deviation gives a measure of spread in the values. So how much the values are oscillating or has spreaded around a particular average value. This was standard deviation in statistics. Then we stated that this standard deviation is related to the uncertainty part in quantum mechanics. Okay. Then what we did? Then I gave you a definition, mathematical definition of what will be the standard deviation in terms of position. So I've given you. So this is the second one. Okay. And then I stated that how this particular mathematics can be related to the uncertainty in position. For example, I gave you the experiment of diffraction, where I've stated that d is the uncertainty in position, and it can be found out, and not found out, it can be related to the spread in the position on the screen. Agreed? And then what I did, and then I just directly instead of using sigma, I just used another quantity, del x. Okay, so that is the uncertainty in position. So I could have written sigma, but just for the sake of convenience, I have written del x. Now this particular quantity del x that you can see on the right hand side can be simplified to this final expression here. Okay. Now why are we simplifying it? The reason we are simplifying the above expression is that we are getting the uncertainty in terms of expectation value, and we know that it is very easy to calculate the expectation value, as a result of which we have done the above simplification. So what we'll do is now we'll try to derive it. Okay, so let us derive it. So start with this. So del x square equals, so just this part. Okay, so what you do is you just expand it. So what do you get upon expansion? You'll get a summation I, just use a square plus b square plus 2ab. So what do you get? So you get the first term as xi square. It's very easy. Second term will be minus 2ab, so minus 2 into xi. Okay, and then what is the second term? That is the average value, that is x bar. What is the third term? Third term is the average value x bar square, all of which are multiplied with p of xi. So what is p of xi? So p of xi is the probability for finding the electron at the position xi. Now question is, you would ask here that, hey, why are we doing things for discrete? Why aren't we doing things for continuous nature? Why aren't we using integration? We'll do that. The reason we are using the discrete pattern is that derivation here is simple with the discrete, and then we will extend the result to the continuous pattern. For example, let us find the result. Okay, so what will happen in the second step? What I can write is summation I. So this will be x I square multiplied with p of xi. Okay, this is the first term. Now before writing the other terms, now can you tell me what is this first term? First term is actually expectation value of x square. So if you go to the lecture series, in our previous lecture series, let me write it on the right. In our previous lecture series, I told you what was the expectation value of x. The expectation value of x was summation I, all the values of xi multiplied with the probability for xi. So this was the expectation value of x in discrete pattern, and it has a continuous way of writing in quantum mechanics that we'll do later on. So first term I've written here. Now can you tell me what is the second term? Now second term is quite interesting. In the second term, what you do is take 2 x bar outside, and then you are left with summation I. Okay, you have x I and you have p of xi. Okay, now can you tell me what is the second term? If you look at the second term very closely, then it is 2 with an x bar, that is the average value. Again we have an x bar. Okay, so instead of writing x bar, what I can do is I can write this as x bar square. Okay, and we know that, uh, so these two things are same. Either you write x bar or you put the bracket and write x bar. These two things are same. So what I'll do is, so for my convenience, uh, I'll just write this as this. Agreed? This square. So this is my second term. Now look at the third term. So the third term will be the x bar square is independent of summation. So this will be outside, and we have summation I over all the probability. Now can you tell me what is the sum over all probability? We know that sum over all probability is 1. That is sum. The total probability is 1 in quantum mechanics. That we already know, total probability is always 1. What is the third term? So third term will be only um, expectation value of x square. Agreed? Again, let me tell you, this symbol and this symbol means the same thing. So what is the answer? So you get expectation value of x square, okay, minus expectation value of x square. Agreed? So our derivation is complete. So what do we get from this derivation? So we learned that we can use this formula to find the standard deviation. Now question is, what is expectation value of x? See, expectation value of x is written here in bit 1. Okay, so what will be expectation value of x square? Okay, so let me write. So expectation value of x square will be so this is second part. Okay, so expectation value of x square will be summation I, okay, x I square multiplied with probability xi. Agreed? Everything is clear by now? Now question is how to write the quantum mechanical version. Okay, so let me delete first. I hope you got the derivation, so I'm deleting the derivation. Please note down the derivation if you have not. Okay, so now the main question is how to write the um, quantum mechanical version. So this is the standard deviation which is correct in quantum mechanical version. Now in quantum mechanics, for the continuous pattern, can you tell me what will be the expectation value of x square? Okay, so in quantum mechanics, what we'll do is we have an integration. You know you have to do psi star psi. Okay, and you have to put x square in between psi star and psi. Agreed? So this is the quantum mechanical version of x square. So what is x expectation value of x? You all know the expectation value of x. It is nothing but integration. You have to put only the value of x between psi star and psi. So you all know this part. Agreed? So when you are asked to square it, then what does it mean? You have to put this in the bracket and then you have to square it. Agreed? So in this way, if you are given a particular wave function psi, please see that if you are given a particular wave function psi, then you can easily calculate this. You can easily calculate this, as a result of which you'll get the uncertainty in position. So the uncertainty in position, the information for uncertainty in position is already inbuilt into this wave function psi. Agreed? So the wave function psi must have the uncertainty in position inbuilt in it. Not only uncertainty in position, it should also contain the information for uncertainty in momentum. Okay, so we'll do that in the next lecture. So I hope you got the clear understanding of how a standard deviation in statistical mechanics is related to the uncertainty in quantum mechanics. Agreed? So we'll continue our lectures next time. Thank you for listening. Bye bye.